Okay, in this lecture we're going to cover the second part of our section 2.4 material on arc length and surface area. And in the first part of this section we had considered the problem of finding the arc length of a curve, which would be the graph of some function of x or y between two endpoints. And we had derived a couple of formulas for the arc length of such a function. So in this second part of the section, we'll consider the problem of determining the surface area of a solid of revolution. So let's consider the following problem. Suppose that we have a continuous function f on some interval from x equals a to b, and we revolve the curve y equals f of x, so the graph of this function, from x equals a to b, about the x or the y-axis. So if we take a curve in the plane and we revolve it about an x or y-axis, we produce a surface, which would be the surface of a solid of revolution, and it's called a surface of revolution. And the question that we're going to pose in this lecture is, what is the area of that resulting surface? So let's consider the problem geometrically. So let's suppose in the xy plane, maybe in the first quadrant, I have the graph of some function, y equals f of x, on an x interval from a to b. And let's say that I take that curve and I revolve it about the x-axis. So if I take a plane curve and revolve around one of my coordinate axes, I'm going to get a surface. So let's see if I can sketch the resulting surface. So revolving this, we would have a surface that looks something like this. And the question is, well, what is the area of this surface? So let's think about how we could find this. If we were to take some small segment of our graph of f of x, shown here in red, which has an arc length, let's call it ds, or actually here I'm going to call it dl for a differential of the total arc length of the curve from point A to point B. So if I divide up my curve into these small segments, the length along each of these segments I could call a differential of the total arc length. And if I were to take that segment and revolve about the x-axis, I get a little strip, a cylindrical strip, which is wrapping around the outside of my surface. So let's see if we could determine the area of that cylindrical strip. So much like we saw for the cylinder method, the method of cylindrical shells for the volume of a solid, we could think about slicing this little cylindrical strip down the middle and unrolling it. And we would have a little rectangular strip. Or let me maybe visualize it like this first before we unroll it. So I would have this red strip is some little cylinder on the outside of my solid, where if we were to cut this strip along one side and unroll it, I would have a little rectangular strip that's wrapped around my solid. And I know how to find the area of this little strip. I would take the length along one of its sides, which would be the total length that I wrap around this cylinder, so the circumference of that circle, which would be given by 2 pi times the radius of this cylinder. For now, let me call it 2 pi r. And then I would multiply by the height of this little cylindrical strip. So this height, the length along this segment, would be the length along this little segment of my curve, whatever this differential of arc length is. Let me call it dl. So the area of this little strip, which is wrapped around my surface of revolution, is what I will call a differential of the total area of this surface of revolution that I'm after. And it would be given by the product of 2 pi times the radius of this cylinder times its height, which is a differential of the arc length. So to get the total area, well, I could integrate this expression, and that would give me the surface area, let me call it SA in my formula below, for the surface area of that surface of revolution. Now there's actually 4 different formulas for the surface area of a solid of revolution, depending on whether the curve we're revolving around an axis is a function of x or a function of y, and depending whether we're revolving about the x-axis or the y-axis. But a general formula for the area of a surface of revolution would be the following. So I'm going to denote it as SA for surface area, and it would be given by the integral of 2 pi times the radius of my little cylindrical strip wrapped around my surface of revolution times the height of that strip, which would be a differential of the arc length of my curve. So here I'm using the notation that capital L denotes the arc length function, and R, which is the radius of my cylinder, is the distance from the curve itself to the axis of revolution. So we can see in this example the radius of our cylinder would be given by the distance from the axis of revolution out to the curve, which in this example is y equals f of x. But in general, depending on which axis we're revolving around, we might have a different expression for the radius. So now that we've derived this generalized formula for the surface area of a surface of revolution, let's look at a theorem where we will consider all of the different cases of revolving a curve around either the x or the y-axis. So this theorem will give several formulas for the surface area of a surface of revolution. So overall, there are 2 primary cases to consider. The first one that we'll consider is if we're revolving a curve about the x-axis, sort of the problem that we were illustrating above. So there's 2 sort of sub-cases for revolution about the x-axis. The first is if we're looking at a curve which is the graph of a function of x, something of the form y equals f of x, where x is between a and b, and if this curve is revolved about the x-axis, the area of the resulting surface is given by the integral from x equals a to b of 2 pi times the radius of our cylinder. So as I illustrated in my figure above, if we have the graph of a function y equals f of x, and we're revolving about the x-axis, then the radius of our cylinder is the distance from the x-axis up to the function, which is what we call y, or here, since y is defined by a function f of x, the radius of this cylinder will be f of x. and then we're supposed to multiply by the differential of arc length. Now, in the first part of this section 2.4 material, we found that if y is a function of x, a differential for the arc length of that function is given by the square root of 1 plus the derivative of that function squared times the differential of x. Now let's suppose that we have a slightly different problem. Let's suppose next that we're considering a curve, which is the graph of a function of y, where y lies between c and d, and we're revolving this curve about the x-axis. So let's see if we can determine the area of the resulting surface. So in general, the area of a surface of revolution is found by integrating. In this case, we would be integrating 2 pi times the radius, which is given by y here. Now let's think about why that would be the case. So if we have the graph of some function of y on a y interval from c to d, and we revolve that curve about the x-axis, well, our radius for this cylinder that we're revolving about the x-axis is going to be the distance from the x-axis up to my curve, which is what we call y. So here, if we have x as a function of y, then we would just leave y as is, because we're going to integrate with respect to y. And then we would multiply by the differential of arc length, which in the first part of this section 2.4 material, we said if x is a function g of y, then the differential of arc length would be the square root of 1 plus the derivative of g squared times the differential of y. And then we would be adding up the area of all of these little cylindrical pieces from y equals c to d. So that is along this y interval. Now, our second case to consider is revolution about the y-axis. So the first sub-case of that is if we have a graph of a function, y equals f of x from x equals a to b, and we're revolving about the y-axis, then the area of the resulting surface is found by integrating 2 pi times the radius, which in this case would be x. Let's visualize it. So if we have some curve in the xy plane, which is the graph of a function y equals f of x from x equals a to b, and we're revolving this about the y-axis, then the radius of this little cylinder would be the distance from the y-axis horizontally out to our curve, which is what we call x. So here we have the integral of 2 pi r, or 2 pi x in this case, times the differential of arc length, which if we're looking at the graph of a function of x, we derived in the first part of this section, the differential of arc length would be the square root of 1 plus f prime of x squared dx. And our final case is if we have the graph of a function of y on some interval from c to d, and this function is revolved about the y-axis, then the area of the resulting surface is given by the integral of 2 pi times the radius, which would be g of y here. So if we take our function, or the graph of our function, something of the form x equals g of y on a y interval from c to d, and we revolve that about the y-axis, the radius of our cylinder would be the distance from the y-axis out to the curve, which is what we call x. But of course, wherever we take this distance, it's dependent on the function, since x is g of y. So our radius here, r, is going to be the value of g of y. So here we're integrating 2 pi g of y times the differential of arc length, which, if x is a function of y, would be given by the square root of 1 plus the derivative of that function squared times the differential of y, and we're integrating here with respect to y from c to d. So in general, there are 4 formulas for the surface area of a surface of revolution, depending on what type of function we're working with and which axis we're revolving around. But an easy way to remember the generalized formula is to think about this little formula for an arbitrary cylinder. In general, we're integrating 2 pi times the radius of our cylinder times its height, which is the differential of arc length. So let's look at some examples of this. We'll illustrate at least one example of each case. So in our first example, we're asked for the area of the surface obtained by revolving the curve y equals x cubed from x equals 0 to 2 about the x-axis. So this one we might even be able to visualize a little bit. If we can graph our function, it may help to visualize it. So we're looking at the graph of y equals x cubed from x equals 0 up to x equals 2. So when x is 0, y, which is x cubed, would be 0. And when x is 2, y, which would be x cubed, is 8. So not drawn to scale here. And then the cubic function would be increasing a little more rapidly than the parabola x squared on that interval. So we're going to take this section of that graph and revolve about the x-axis. So we get this surface shown here. And the question is, what is the area of this surface? So let's take a look at this. To get the surface area, we're going to be integrating 2 pi times the radius of our cylinder. So in this example, if we're revolving about the x-axis, the radius of our cylinder will be the distance from the x-axis out to the curve, which was the curve defined by y equals x cubed. So here we're going to have 2 pi times the radius of our cylinder, which is x cubed, times the differential of arc length. So here, if y is a function of x, we would have the differential of arc length given by the square root of 1 plus the derivative of our function. So if y is x cubed, our derivative would be 3x squared, squared times the differential of x. And here we're integrating with respect to x. So let's think about our limits of integration. Along the x-axis, we're moving from x equals 0 to 2. So those will be our limits of integration here. So once we set up our formula for the surface area, let's, as we did in the case that we were looking at the arc length of a function, try to simplify the expression under the radical. So that is this expression under the square root. We want to simplify as much as possible before we integrate. And in general, for these problems on arc length or surface area, that's typically how we want to proceed. After we set up this integral, your next step is to simplify that expression under the radical as much as possible. So here we have 2 pi times the integral from 0 to 2 of x cubed times the square root of 1 plus, squaring this term, we have 9x to the 4th dx. And that's as far as we can simplify. So our next step here, since we see that our integrand involves a composite function, would be to try a substitution. So the substitution that I'm going to use is to let u equal the inner function in my composition, 1 plus 9x to the 4th, in which case du would be 36x cubed dx, and so dx is equal to du over 36x cubed. So let's rewrite our integral for the surface area in terms of u. So we had this constant 2 pi out in front of our integral, and in our original integral, the lower limit of integration was x equals 0. So if we take x equals 0 and we substitute into the formula for u, we would find that u is 1. So that will be our new lower limit. And the upper limit in the original integral was x equals 2. Substituting 2 in for x, we have 2 to the 4th, or 16 times 9, plus 1, which gives us 145 for our u value. And now we had an x cubed times the square root of u, and the differential of x dx is equal to du over 36x cubed. So after making the substitution, we can see a factor of x cubed on top and bottom will cancel. And then I can group the constant terms, 2 pi with this 1 over 36, which would give me a pi over 18 out in front of the integral. And then I have the integral from 1 to 145 of the square root of u du. So for our antiderivative, we have pi over 18 times the antiderivative of square root of u is 2/3 u to the 3/2 power, which we're evaluating from 1 to 145. So in our last step, we'll simplify the constants a little bit. Here we would have pi over 18 times 2/3. Well, I can cancel a factor of 2 on top and bottom. That gives me pi over 9 times 1/3, or pi over 27. And then when I evaluate this antiderivative, u to the 3/2, or u times the square root of u, at the upper limit, 145, I have 145 to the 3/2 power, or 145 times the square root of 145, minus the value I get when I substitute u equals 1 into the antiderivative, which would be 1 to the 3/2, or 1. So this expression would give me the surface area of that surface of revolution that we were considering here. So let's look at some other ones. In this next example, we're asked for the area of the surface obtained by revolving the curve, x equals 1/3 y squared plus 2 to the 3/2 power, where y ranges from 1 to 2 about the x-axis. So let's set up our integral for the area of this surface. In general, we know that we're taking the integral of 2 pi times the radius of our cylinder. So if we're revolving about the x-axis, the radius of our cylinder is going to be the distance from the x-axis up to our curve, which is what we're calling y. And in this case, since x is a function of y, we would leave this as y instead of, as in the previous example where y was a function of x, we could plug in that expression for y. Now, we have 2 pi times the radius of our cylinder so far. We're supposed to then multiply by the differential of arc length. So here x is a function of y, and we need to find the derivative of this function. So a little scratch work to the side here. To find the derivative of this function, we would need to use the chain rule. So the derivative of the outer function would give us a 1/2 of y squared plus 2 to the 1/2 power. And then we multiply by the derivative of the inside function, which would be 2y. So simplifying a little bit, we have a constant 1/2 times the 2y would give us y, and then y squared plus 2 to the 1/2 is the same as the square root of y squared plus 2. So for the differential of arc length, we have the square root of 1 plus this derivative, which we just found as the following. Quantity squared, and we're integrating with respect to y. Now let's think about our limits of integration. We were told here that y was between 1 and 2. So we will integrate with respect to y on that y interval from 1 to 2. So now that we have our integral for surface area set up, our next step, I mentioned, is to try to simplify under the square root as much as possible. So here we have a 2 pi times the integral from 1 to 2 of y times the square root of 1 plus, when we square this derivative term, well, we have a y squared, and then the square root of y squared plus 2 squared gives us just a y squared plus 2. So now under the radical, if we continue to simplify, we have the square root of 1 plus, if we distribute the y squared term, we have y to the 4th plus 2y squared dy. And in order to explain my next step maybe in a little more detail, I'll add one extra step here. So I have under the square root, if I just rearrange the order of the terms, I'm going to put the y to the 4th power first, then plus the 2y squared, and then plus 1 dy. So I'm just going to rearrange those terms, and the reason is to explain my next step. So if I now look at this expression under the radical, I can recognize that it factors as a perfect square. So I'm going to have 2 pi times the integral from 1 to 2 of y times the square root of, now this polynomial with respect to y can be factored as y squared plus 1 quantity squared. And then I've got my dy on the end. So when I take the square root of that expression, I'm left with 2 pi times the integral from 1 to 2 of y times y squared plus 1 dy. Or distributing the y, I have 2 pi times the integral from 1 to 2 of y times y squared is y cubed plus y times 1 dy. So we now have a 2 pi, and at this stage I can find my antiderivative. So the antiderivative of y cubed would be 1/4 y to the 4th, plus the antiderivative of y would be 1/2 y squared, and we're evaluating the entire thing from 1 to 2. So let's see what we're left with. We have a constant 2 pi out in front, and then we are multiplying by the value of our antiderivative at y equals 2. So here we would have 2 to the 4th, or 16 times 1/4 is 4, plus 2 squared would be 4, taking half of that gives us 2. And then I subtract the value that I get when I evaluate at y equals 1, which would be 1/4 plus 1/2. So simplifying, I have a 2 pi times the 4 plus 2 gives me a 6. And then I'm subtracting 1/4 plus 1/2, which would be 3/4. So altogether, this leaves me with a 21 pi over 2 after a little bit of simplification. So in these first two examples, we're calculating the area of a surface obtained by either revolving the graph of a function of x or a function of y about the x-axis. So let's look at some other examples with revolution about the y-axis. So in this next problem, we're asked to find the area of the surface obtained by revolving the curve y equals 1 minus x squared from x equals 0 to 1 about the y-axis. So this function is pretty simple. We could actually sketch what we're looking at here. So in the xy plane, we have the graph of 1 minus x squared, which would be a parabola whose vertex is at 0, 1 and opening downward, crossing the x-axis at 1. So we're looking at this curve here. And then we're revolving it, we're told about the y-axis. So when I revolve this about my y-axis, I'm going to get this little surface of revolution, and the question is, what is the area of this surface? So let's use our formulas to set up an integral for this surface area. So in general, to find the surface area for a surface of revolution, we're going to integrate 2 pi, which I can always pull out in front of my integral, times the radius of our cylinder. So here, if we're revolving about the y-axis, the radius of our cylinder will be the distance from the y-axis out to the edge of my function, which is the horizontal distance x. And here y is a function of x, so I'm just going to leave it as x. And then we have to multiply by the differential of arc length. So that would be the square root of 1 plus the derivative of my function. So here, if y is 1 minus x squared, y prime is going to be negative 2x. We square that quantity. And then we're integrating with respect to x on the interval x equals 0 to 1. So here our limits of integration will be 0 and 1. So as with our earlier examples, once we set up this formula for the surface area, or our integral for the surface area, we want to simplify under the square root as much as possible. So in this case, I would have 2 pi, the integral from 0 to 1 of x, times the square root of 1 plus 4x squared dx. And this is as far as I can simplify. So in order to integrate this, since my integrand involves a composite function, I would need to use a substitution. So here, the substitution I'll make is to let u be the inner function, 1 plus 4x squared, in which case the differential of u would be 8x dx or dx is du over 8x. So let's rewrite our integral for the surface area in terms of u. So out in front, I had a constant 2 pi. And since this was a definite integral, I've got to change my x values to u values. So in the original integral, my lower limit of integration was x equals 0. If I substitute that into my expression for u, I have 1 plus 4x squared. So if x is 0, that would give me 1. And my upper limit of integration was x equals 1. Substituting that into the formula for u, we would have 1 plus 4 or 5. And then I had an x times the square root of u. And the differential dx on the end, we found is du over 8x. So here we can cancel a factor of x in the numerator and denominator. And grouping our constants together, well, we had a 2 pi out in front. When we made our substitution, we had a factor of 1/8. So taking a 2 pi over 8, we have a pi over 4 out in front, times the integral from 1 to 5 of root u du. So at this stage, we can find our antiderivative, which would be pi over 4 times the antiderivative of square root of u is 2/3 u to the 3/2. And we're evaluating from u equals 1 to 5. So simplifying our constants, we had a pi over 4 times 2/3. So that's 2 pi over 12, or pi over 6, times, when I evaluate this u to the 3/2 at 5, I have 5 to the 3/2, or 5 times the square root of 5, minus 1 to the 3/2, which is 1. So this would be my area of that surface illustrated in this example. Now for our last example, we'll consider the problem of finding the area of the surface obtained by revolving the curve x equals 2y minus y squared, where y ranges from 0 to 1 about the y-axis. So here a little difficult to sketch. We may not know immediately what that curve looks like. So let's not sketch it here, but let's set up our integral for the surface area. Now generally, we're taking the integral of 2 pi times the radius of our little cylindrical strip, which would be, if we're revolving about the y-axis, x, that is the distance from the y-axis horizontally. But x in this problem is given by a function of y. So our radius is going to be this function, the square root of 2y minus y squared. And then we're multiplying by the differential of arc length, which would be the square root of 1 plus the derivative of this function squared. So a little scratch work to the side here. To find the derivative of this function, we're going to have to use the chain rule. So recall that the derivative of the square root of stuff is given by 1 over twice the square root of stuff. So for the derivative of the outer function, we would have 1 over twice the square root of 2y minus y squared. And then using the chain rule, we have to multiply by the derivative of the inner function, which would be 2 minus 2y. So simplifying just a little bit, well, when I have 2 minus 2y and I'm dividing by 2, I can cancel out a factor of 2 in the numerator and denominator, and that would make my numerator 1 minus y. and my denominator is the square root of 2y minus y squared. So in my formula or in my integral for surface area, I have the square root of 1 plus that derivative that we just found, squared, and we're integrating with respect to y, over the interval y equals 0 to 1. So those are going to be my upper and lower limits for integration. So as with our previous examples, I mentioned that we want to simplify under the square root as much as possible. So let's see what we have here. Out in front, we've got our 2 pi times the integral from 0 to 1. And we've got the square root of 2y minus y squared times the square root of 1 plus, when we square this, our numerator will be 1 minus y squared, and then we're dividing by the square root of 2y minus y squared squared, which gives us 2y minus y squared. Still have our differential of y on the end. So what we can do now is the following. We're multiplying two expressions involving the square root of a quantity. So we can group those together as the square root of the product of that quantity. So instead of multiplying the square root of these two separate expressions, we can take the square root of the product of these. That is 2y minus y squared times 1 plus 1 minus y squared over 2y minus y squared, dy. So that is, we're using the fact that the product of the square root of two terms is the same as the square root of the product of those terms. So now, under this single square root, let's continue to simplify. And we can see here that when we distribute the 2y minus y squared, we have 1 times 2y minus y squared. And then plus, when we have 2y minus y squared and we multiply by 1 minus y squared over 2y minus y squared, these terms will cancel, and we're just left with that 1 minus y quantity squared. We still have a dy on the end. So continuing to simplify, we have 2 pi times the integral from 0 to 1 of the square root of 2y minus y squared plus, when we expand this, we would have 1 minus 2y plus y squared dy. And we can see that under the radical, we have a 2y and negative 2y that cancel, and a negative y squared and positive y squared that cancel. And so we're left with 2 pi times the integral from 0 to 1 of the square root of 1, which is simply 1, dy. So at this stage, it becomes easy to integrate. We have 2 pi times the antiderivative of 1 with respect to y would be y. We're integrating from 0 to 1. So we have our constant 2 pi times, when we evaluate at y equals 1, we get 1, minus when we evaluate at y equals 0, we have 0. So finally, we're left with a surface area for that surface of revolution given by 2 pi square units.